the second talk of the morning, we have Mark Braverman, also from Princeton, but from the computer science department. He did his PhD here in the University of Toronto before going to MIT, to Microsoft Research Lab, and then coming back to Toronto because Toronto is a great attractor. And, but Princeton stole him away. He has given talks at the ICM in 2014, and then most recently in 2022, where he was awarded the Abacus Prize. So today he's going to talk on communication and information complexity.
Thank you. Thank you for organizing this beautiful conference, and thank you for inviting me. So I'll talk about communication information complexity since it's a broad audience talk. This question came up yesterday also in the panel. What is computational complexity in 2 slides at the mathematical level? So the 2 main tools that we use and develop is abstraction and reduction. So abstraction, we build models of computation, and you'll hear about 2 of those today. So Turing machine is a model, but communication complexity is also a very useful abstraction that abstracts part of the computation to get some useful and interesting results. And the second tool that we use extensively is reduction. So reduction connects 2 statements that we can remain agnostic about the truthfulness of either one of them. So a typical reduction, if I could solve problem A, then I could also solve problem B. And it's very useful a lot of the time when you say, if you say that something is NP complete and you don't have to bother, you're using the contrapositive. If B is difficult, then so is A. And so, for example, if you could predict the future with this magic ball, you could win the lottery instead of offering your services for $50 a piece. So that's a reduction from winning the lottery to predicting the future, which is very useful in the contrapositive. And it allows us to consolidate conjectures. So instead of having thousands of conjectures about this problem is hard, this problem is hard, we can consolidate them into still hundreds, but not hundreds of thousands of questions. So communication complexity is one such abstraction that it's maybe not as well known as time-based complexity classes, but it's actually very useful because we can actually prove a lot of unconditional results. So in the most basic setting, we view the input as partitioned between 2 parties, could be more than 2 parties. And then, we need to compute some function, we'll just look at the input. And then we abstract away computation that happens inside each party, because computation is too hard to reason about. We only focus on communication between the 2 parts. And this is highly non-trivial, but usually we can say a lot about. So a lot of interesting action happens there. And there we can lower bound the amount of communication, which we can then use to lower bound some kind of notion of activity that's needed to perform the computation. And it's a very useful tool for obtaining unconditional lower bounds in many areas, or at least, again, consolidating questions into conjectures that are not the kind of conjectures that we hope to solve in the next 20 years, as opposed to the kind of conjectures that are a safe way to park $1 million. So in many areas of like circuit design, where communication between parts of the chip, market and mechanism design, where a market is a kind of communication mechanism between parties, you can get unconditional lower bounds using reductions to communication complexity. So that's a crash course on why. Now let's focus on the possibly simplest model. There are 2 players. They're usually named Alice and Bob. And they want to do something, compute some function f or implement some functionality. So at the end of this process, they want to have accomplished f. The tool they use is called the communication protocol, which is just a sequence of functions. So we usually allow them to use randomness, sometimes, oftentimes. And a communication protocol is just a sequence of messages where each message can be derived from my own input and what I've already heard. So the first message depends on Alice's input. The second message depends on Bob's input and the first message, and so on. So it's just formalizing a conversation. And the cost is the number of bits exchanged. So now we can talk about, again, this is the communication cost of a protocol. The communication complexity of a problem is the least amount of resources you need to solve this problem. So you minimize overall protocols, the communication cost that get the job done, the communication cost of that protocol. And in most cases, you don't, in this entire talk, there is always kind of a trade-off between writing definition and not writing definitions. You don't need to read any of the definitions as long as you believe me that there are definitions. So, but yeah, so here, this is a human readable. Complete the task within the acceptable parameters while exchanging as few bits as possible. And so that's the goal. So this is a kind of canonical example that's hard, but not too hard. We have many proofs for it by now, but it's a very useful example, set disjointness. So Alice and Bob have each a bag of k animals out of n possible species, and they need to decide whether they have an animal in common or not by a communication protocol. So here they do have a panda in common. So a trivial upper bound is Alice just enumerates all the animals in her bag. That takes k log capital N, because log n is the number of bits you need to name an animal. And then there are k animals in your bag, so that's the trivial upper bound. In fact, if you get completely bored, this is by the rest of the talk, this is a fun exercise. How do you do it with k bits, with order k bits? Instead of, you can save this log n factor using tricks like hashing. So this is the upper bound. It turns out that this upper bound is tight, which is, maybe it's not surprising if you're used to it, but you could expect that you could do something clever and maybe go below k, especially after you manage to go from k log n to k. But in fact, k is the true answer. So even when n is 3k, disjointness requires linear communication. Well, with 3k, it's just a bit string, so it's obvious that it's at most linear, but it's actually tight. And this is a very important building block in many other unconditional lower bounds, because many problems are harder than disjointness. So you could make statements of the form, if I could solve this, I could solve disjointness. And so that requires linear communication. So there are many approaches based on algebra, based on other ideas. The most direct approach is something called based on direct sum. So we look at the problem and we realize that it's actually n individual decisions, right? So it involves, let's say, n is 3k. There are 3k decisions of the form, is animal I in both x and y. So we just need to make those decisions. And so is the peacock in both? Is the rabbit in both? Is the tiger in both? So there are 3k. So we could hope that the cost of disjointness is 3k times the cost of each of these boxes. And then to complete this proof, so the nice thing is that we haven't worked hard so far. We were more aspirational, but we didn't need to do anything yet. So we need two things to happen. We need the cost to add up, and we need the cost of each box to be constant. And in this case, this is actually both are true. So this is, in general, this is a generic type of statement in computation, and you can see why it's a desirable property if you're in the business of lower bounds. If a task T costs C resources, then K independent instances of T cost at least K times C. And these types of statements, they're useful to make, to make hard problems harder. There are two reasons why we would want to do it. One reason is because we are complexity theorists and we want to prove lower bounds. But actually, the second, where it's actually used in practice, is in cryptography. If you want to amplify security, it's not obvious. So for example, it might be more secure. So some amplifications are more secure, like asking you to lengthen your password makes it more secure, but asking you to input your password 3 times in a row doesn't make the system more secure. So this is a hardness amplification for cryptography is a real thing. So it's important for both of these reasons. Okay, so that's direct sum. And strong enough direct sums would actually lead to strong circuit lower bounds and actually chip away at things like P versus NP, like the Karchmer-Wigderson program. It fails kind of in a very mysterious way in many cases. So here is an example of direct sum not working in a kind of fairly mysterious way. So here it's circuit complexity. I fix a matrix and I want to multiply a matrix by a vector. So just by counting, there are 2 to the n square matrices. So you need roughly 2 to the n square circuits. So even if I fix A and I want a circuit for computing AX, I need roughly n square gates. Maybe you can shave off a log, but that's basically the said truth. What about computing A times many x's, like n? Well, that's matrix multiplication. So I can actually build a circuit for, if you give me n x's, I can do it in n to the omega, which is, we don't know what it is, but we know that it's a lot less than n cubed. So you can solve n copies of A times x in a lot less. So direct sum kind of fails. In this case, maybe it would fail in many interesting enough computational models, but what about communication complexity? So, and the source of envy and inspiration is Shannon's information theory, where statements like this are true. So here is, a lot of those results are really old, from the 40s and 50s, but the basic idea that in coding theory and information theory, so the basic goal is data transmission as opposed to computation. There are different communication channels. There is a big, both for practical and theoretical reasons. We have models of computation and computational complexity. Big questions, so pretty much are answered by theorems. And moreover, the theorems are very precise. So if you specify a channel and a task, you can actually compute up to lower order terms the amount of resources you need. So there are second order questions, but to the first order, everything is solved. Whereas our gaps in computational complexity, it's not that we don't know if it's 5n or 5.1n. It's usually that we don't know if it's 5n or 2 to the n, like for solving SAT. So that's at least trying to move the needle towards expanding kind of this world at the expense of this type of world. So a key concept in Shannon's information theory is Shannon's entropy. Again, mostly I'll write some definitions. The goal is to know that there are definitions. So there is a message X distributed according to some prior distribution mu. And then the entropy measures the inherent amount of bits it takes to transmit X. And there is a formula for it. And Shannon's noiseless coding theorem says that the cost of communicating many copies of X scales like H of X. So if C of n is the cost of transmitting n independent copies of X, then this limit is H of X. And this makes, so you could say that anyone can write an expression with logs. This gives it a meaning that is real even if you don't like logs. So now you have to care about logs because this is something that exists in the real world. So, and H is nicer than C. So if you were unlucky to kind of, the world of C feels like hardcore combinatorics. The world of H is actually nice and algebraic. So let's say sending a uniform treat. So you get a number between 1, 2, and 3. The best encoding for sending one treat, if you're being honest, is 5/3. Using bits is 5/3 bits, and sending 2 is, if you just draw the right tree, it's 29/9. So for example, you get savings. So direct sum kind of slightly fails here, right? So 5/3 plus 5/3 is less than 10/3. It's 29/9. So direct sum fails. But for entropy, it's just entropy of 2 independent treats is log 9, which is 2 log 3. So life is much nicer. So direct sum holds, and of course it holds in the limit. And so this is what we wish happened in more models of computation. So let's at least try to make it happen in communication complexity. So it takes a little more information formalism to make it happen there. So in addition to entropy, there is something called conditional entropy, which is if X and Y are two random variables, they're correlated somehow. How much entropy is on average left in X if I tell you Y? Mutual information is how much entropy Y reveals about X, how much we learn about X if we hear Y. You can mix those. There is conditional mutual information. Again, how much does Y teach? So this statement here tells us how much does Y reveal about X to someone who already knows Z. So it's again, there are more annoying ways to express it, which are precise, but we don't need to worry about it. So now we arrive at how do we measure the cost of the protocol? Let's not worry about bits transmitted because bits are not as nice. Let's talk about information directly. So the information cost of a protocol is how much is what the parties learn, the two parties learn from the conversation. So it's what the protocol reveals about Y to Alice, who knows X, plus the corresponding second term. And it depends both on the prior, of course, and on the protocol. So you could make it 0 by saying nothing or by already knowing everything. So if, for example, if Alice and both know X and Y, so it's mu is a singleton, nothing that they say will reveal any information. And now you can apply it to the problem, reveal as little information as possible. I don't care how long you talk as long as you don't say anything. Solve the task while revealing as little information as possible. In fact, the first reference I found when this type of expression was written by cryptographers who wanted to do this for secure computation reasons, not for kind of not for efficient communication, but for secret communication. And so the analogous, the only difference is now you need an infimum because it's possible that the more you talk, the less you say. And it actually happens with very simple functions already. So you need this infimum. And it's in the lower bound land, we are in good shape because it is a lower bound on communication. I mean, you never reveal more bits than you say. Sometimes you reveal a lot less. And it turns out that it is a scaling limit if you set everything right. It is the scaling limit of communication. More generally, it satisfies direct sum. So it adds up. The information complexity of two tasks is the sum of information complexities of individual tasks. And in particular, direct sum for communication complexity holds if and only if communication complexity and information complexity are roughly the same, because this is the scaling limit of communication, and it's equal to it's close to communication if and only if those two are close, which brings us to interesting questions about whether you can compress every conversation, but we won't go there in this talk. Instead, observe that if you want, as we do, to understand specific problems like disjointness, you can work with information complexity directly. So that's the tack that we'll take here. So let's look back at the animals. So we want to decide if they have an animal in common. So we have those boxes here deciding whether each element is in both X and Y. The information from the theory we discussed so far, we get that the communication complexity of this problem is very close up to lower order terms to the n times the information complexity of the n function. So just the 2-bit n function. And mu is each animal is added with some small, you have to be careful about what mu is, because of course, n might become harder if it's likely that they both have an animal, but then the big problem will be very easy if they have a lot in common. So you have to add each animal with a tiny probability, but and then now it's a problem about a function with 2 bits, which is, it's interesting that it's still a meaningful question. We want to compute the 2-bit end, which is the only kind of interesting in some way function on 2 bits, all that up to change of variables. So we want to understand how to compute the end function while revealing as little information as possible. And it turns out that this question has a specific answer, and it's actually, once you recompile it, it's actually a pretty natural protocol. So here's how to compute the NN function while revealing as little as possible. The only assumption here is that mu is symmetric, that the probability of 0, 1, and 1, 0 are the same. Otherwise, you need to make an extra step. But so here's what you do. If you're Alice, we'll come up with a real variable. So the real, if x is 1, that variable is 1. If x is 0, then you sample a uniform number, real number between 0 and 1. And Bob does the same. And now there is a clock running from 0 to 1. You find your number on the clock. So this situation corresponds to 0, 0. This situation corresponds to 0, 1. You let the clock run. When your number is called, you raise your hand. And that's the protocol. So if someone raises their hand before the clock hits 1, then the answer is 0, because that person confessed to having a 0. If the clock runs all the way to 1, then the answer is 1, because both players have a 1. Kind of a couple of observations, so the first one, actually, if all you wanted is a linear lower bound on the cost, observe that the only way to be sure that the end is 0 is for someone to confess. And that reveals a constant amount of information to the other player who was uncertain about their bits. So that's already enough to prove a linear bound on disjointness. But now we are pretty ambitious. We want an exact bound. We want to know the constant. So then we need the perfect protocol, which turns out that this is it. The gain comes from, so one person confesses, in this case, Alice confesses, but the gain is that she's, at this point, the whole world knows that Alice has a 0, but Alice still has some uncertainty about Bob. She's more inclined to believe that Bob has a 1 because Bob hadn't confessed here, but there is still a fair amount of uncertainty, and it turns out it's the optimal amount of uncertainty you can have. So that's the protocol. Then you calculate how much information it reveals. Turns out that in this regime, you get the constant is 2 over ln 2 times k. So that's the final answer, is that this is communication now, not information. Up to lower order terms, you need 2 over ln 2 times k communication to solve this problem. So this is asymptotically optimal. It would be hard to discover directly because there is no kind of natural combinatorial interpretation of this. Moreover, it's not, what I described is not even a protocol, right? Because it's continuous clocks, and I said you have to exchange messages. So you do what a real clock does, you discretize it. When you discretize it, you lose something, because if they hit the same point, then something awkward might happen. So you need to get optimal, you need omega-1 rounds, and you lose some constant, something like k over r squared communication. If you use a constant number of rounds, it's a diminishing additive term, but it's a first order term nonetheless. So far, okay, so let's summarize the story so far. So we have a two-party information complexity, which is an interactive analog of Shannon's entropy, and it gives us a handle on the direct sum question, at least in this setting. And now there are a lot of connections. So actually, there is a choice of kind of which connections to present. So again, all the applications from before and a few more. So private computation comes up naturally, and something called parallel repetition and connections to geometry actually. So yeah, so there are all kinds of interesting connections. Let me just talk about one, because now in the last 10 minutes, it's natural to talk about like where are we stuck? Why haven't we proven P not equal in P yet or something? So we are stuck at three parties actually, and it's more interesting almost why we are stuck than kind of getting unstuck, because if we get unstuck, we'll just get stuck somewhere else. But understanding the obstacles and the fact that they kind of come in all kinds of flavors, so I can explain in at least two different languages why we're stuck. So in computer science language, we are stuck because of something called secure multi-party computation. So it turns out that with two parties, basically the same results, that also tell you that if Alice and Bob don't trust each other and they need to solve disjointness, that's tough luck. They'll basically have to reveal as much information about their inputs as whatever communication is needed. Of course, in practice, you can bypass it with cryptography, but that wouldn't be information theoretic security. That would be cryptographic security. So they don't learn anything, assuming they cannot break some crypto system. But information theoretically, there is nothing you can do. In three parties, there is this miracle that basically everything is possible. So three parties, as long as they're honest, let's say in the honest, but it's called the honest but curious model, three parties can compute anything without revealing anything to each other except for the answer. It's also if you want a perfect scheme, it's hard, but it's actually a nice exercise kind of to try to come up with a solution to this on your own if you haven't seen it. And this is obviously a problem for us because it means that anything, actually you can write everything we did for two parties, you can write it for three parties, it will be true. It will be 0 plus 0 equals to 0, which is, it's true but not useful because it's no longer a sound lower bound. And in math language, it's actually still very tempting. So if you are not hung on constants, everything we've done so far you could redo with matrices. You'll lose some constants, but basically you'll be using the fact that matrix norms, many natural matrix norms tensorize. 3D tensors are harder than matrices, and maybe it's something I'm trying to pitch to this audience because maybe it's not as hard. Maybe some progress can be made abstractly still. But here is a concrete question. So this is called the GHZ game. It comes from quantum information theory. It's not, don't try to find reasons. So it's been designed for a purpose. So it's not a game that you'd want to play for just for fun, but here it is. There are three players now. They get in an input uniform subject to the XOR of the inputs is 0. So it's either all of them get a 0 or two of them get a 1 and one of them gets a 0. And each of them output, so they don't talk to each other at all. There is no communication. They output, each of them outputs a bit, and they win the game if the XOR of the bits they output is equal to the OR of the input. So basically, they have to output bits that XOR to 1 if the inputs were two ones, and they need to output 3 bits that XOR to 0 if the output was all zero. So that's the game. It's not hard to see. It's not a very complicated game that the best strategy gives you a 3/4 success probability. The best strategy is to ignore your inputs, hope that that the input wasn't 0, 0, 0 and output 1, 0, 0 or something. So that's the best strategy. What makes this game interesting is if Alice, Bob, and Charlie are quantum now, then there is a strategy that wins with probability 1. And that's the reason this game was invented. So it's kind of like, so there are weaker Bell inequality violations like SH games where it's, let's say, classical players win this probability 3/4, quantum players win this probability 85%. This is much more impressive. So quantum people never lose, classical people lose with some probability. So it's a more impressive experiment. And now the question is, can we make it even more impressive by creating n GHZ challenges? What will happen if instead of just asking 1 bit each, I'll give each player an n tuple of bits and treat it as n experiments and ask what happens with the probability of success. So with quantum entanglement, it's still 1. Without quantum entanglement, it was open for a while, and it was kind of the easiest problem of this sort that we had no handle on, of what happens to the value when you ask many challenges in parallel. Because it's obvious that you can win with probability at least 3/4 to the n, but it's not obvious at all. And in fact, we weren't even sure if it's true or not, that the success probability decays exponentially. Maybe you can do something clever and win with much higher probability by kind of correlating your answers in some way across copies. And in fact, the proof uses additive combinatorics. And the question is there a completely elementary proof that uses just tensors? So what would a tensor-based approach look like? So here's a matrix. It's kind of the second simplest matrix after the rank 1 matrix. It's roughly corresponding to an AND function. So it has a spectral norm well, all I need is that it's smaller than the spectrum norm of the one that has a +1 there, +½ there. In particular, when I tensorize it with itself, the norm goes down exponentially, which is kind of an obvious fact, but you don't appreciate your blessings until they're taken away from you, like with tensors. So that's true. And it already implies some kind of statement exponential decay statement for a 2-player game, kind of similar to GHZ. It's, it's not the best statement you could get, but it already implies a good enough statement. So the corresponding tensor-based question is this is a 3D tensor corresponding to the GHZ games. You see it's a 3D, so it's a 2x2x2 tensor. It has half the numbers are 0 because half the inputs are inadmissible, and the other ones, one of them has the opposite sign. And it's a natural algebra question. Is there a tensor norm that bounds success probability of strategies and tensorizes in some natural way that corresponds to many copies of a game? So far, so last time I gave this talk, I was more optimistic. I had a candidate for a norm. That candidate had failed. So that was, but on the other hand, now this is a theorem. So we know that the scaling is true. So it's just finding a second proof to a theorem is easier than finding a first. So it's less discouraging. So there should be some norm in the so to at least make progress in the math language. And I suspect that this is kind of an easy toy problem, but I suspect that progress on it will translate into progress into places where we are stuck in both languages right now. So to get around so on the computer science side, we need a new information theoretic definition that doesn't collapse to 0 because of secure multi-party computation. or new analytic tools with 3D tensors. And we have kind of a lot of a good blueprint in both languages with matrices and with information for the two-party case. Or all of this might fail. We know that eventually it's a bit of a tragic enterprise in the sense that understanding computation, like in general, is very hard. Maybe we'll find that communication where we understand everything ends and computation begins sooner than we thought. But even that, it should be interesting. So that's where we're at. Thank you.